Okay. Okay,ครับ. Last week we talked about data mining. Just to give you, I don't know if I did mention, after you've done all the data mining, the way you use it is really like pairing stuff. Okay, like things tend to go together. So chances are, if bread and butter goes together for most of the population, then somebody who just bought butter would probably like to buy bread, that sort of thing, right? So we talk about that, and to be honest, I'm not gonna go over data mining in that form probably again. Now, let's do this. Okay, let's start fresh. Okay, so I want everybody to kind of oh, what's this? Okay, let me turn off everything and start from nothing, start from scratch. Okay, right. The first thing that we are going to do, okay, let's start from scratch. Okay, you recall that old faithful data, right? So this is the example data. What have we got? Example data. I think it's statistics, right? Again, it's gonna be this kind of thing, where you just kind of use oops. Sorry. Now, sample statistics. What have you got? So many things. So I'm gonna get. I think it was all faithful, right? Oh, there it is. Right. So, now let's call this our data. So I can refer to it. Actually, let's do this so I don't have to see it. Okay. Dimension. I always do this before. In fact, by the way, this is my style of programming. If I want something named and I want some immediate information, I would just do this in one line like this. Okay. You don't have to do this. This is my style. Okay. Yeah. So dimensions of this thing, and instead of I just might as well name it all in one line. So okay. So it's got 272, right? 272 of two numbers. Okay. And when we list plot, say list plot, right? So we can say list plot. Okay, you got this, right? Okay. Now, here's what I would like to do. I would like to do. Okay. Obviously, to your eyes, okay, it has two clusters. Okay. The first thing we're going to learn is called clustering. Okay. So let's think of making up some data to cluster. Now, in this case, if we do some kind of histogram 3D, right? We did that, right? I think. Okay, we got this. Okay, fine. So obviously, to your eyes, it's obvious that the two cluster, right? So when you have to wait for a long time, the hot water fill a bigger cavity. So when the spout shoots in the air, it lasts a long time. So wait a long time, gets a longer show. Wait a short time, get a shorter show. So that sort of thing. So what I want to do is like this. Now, it's like this. It's the data like this. So if this were a statistical exercise, okay, if this were a statistical exercise, well, let's just look at one dimension. Let's look at one dimension. Okay, let's say histogram data. Now let's look at all of them, but I look at the first one. So first one I think is how long it lasts, right? 5 minutes or whatever. So let's make it a little bit more details. Add number of bin. Oh, no, it's not. Okay, so it's not very detailed. So sometimes you wait for sometimes you get a 1 minute, 2 minutes of spouting of the old faithful shooting the water. Sometimes you get 4 minutes, 5 minutes. So that's looking at this. Now, what would a statistical approach to modeling this thing be? Just one dimension. 2 dimension, we'll come to it, but just 1 dimension. Okay. Now, mathematician gave you, right, a whole bunch of them. First of all, you know that this is not negative, right? This is not negative. So if I were to do this, say, go to a Google Wikipedia page, right? Just now, where's the Wikipedia page? Okay. So it would have to be something like support on semi-infinite. Okay. Semi-infinite. And one of the things that I told you is going to be useful a lot is gamma. Let's go to gamma. Gamma. Okay. There. It's gamma. Okay. So based on what I told you earlier, what is your job? Your job is to choose probability distribution wisely. Okay. So what do I choose? This is my histogram. I'm going to choose one of these to fit. Okay. Now, because gamma is such a useful thing, such a useful thing, but it has a limitation. It's what's called unimodal. Okay. Meaning that it doesn't repeat. That's the limitation. So let's think of it. We have a limitation. Now, one of the useful thing is, well, I'm just going to go ahead and tell you the answer. Okay, so just on this dimension alone, okay, on this dimension alone, okay, I can ask Mathematica to find the best distribution. Okay, so again, I told you that there are 10 of them, but we have machine. We might as well ask Mathematica what's the best fit. Okay, and that's done by doing this. Find distribution. Okay. Now look at this. It actually doesn't give you 1. It gives you 2 in combination under the word mixture distribution. What this means is that instead of treating individual distribution function here, okay, some of this, whatever it is, on bottom of gamma, you also have the same menu. Where's the menu? There, right? Instead of taking just one of them, how about we allow composition? This is called mixture distribution. Okay, so you can think of it as, instead of having 1 gamma, just take 1 gamma plus another, I don't know, logistic. I don't care. Maybe take 2 gamma. And that's what this mixture distribution is. Okay, the mixture distribution gives you choice. Okay, 1 distribution here, 1 distribution here, with a kind of Bernoulli or coin toss. 35% this, 65% that. Can you guys see this? Okay, let me draw from scratch. Okay, let me draw from scratch. Let's say I want to plot okay, PDF of, okay, I'm just going to take this guy, log normal distribution. Okay, this is my log. So the full name is this, okay, of x, right? And x from 0 to 10. PDF. Oh, I have extra. Okay, can you guys see this? Okay, I'm going to plot, okay, a PDF. Okay, let me just take the decimal point away. So, okay, log normal distribution takes two parameters. These are the knobs. Okay, this guy, right? 0.7 and 0.1. I'm gonna make PDF of this function. So mathematically, this is my distribution of x given parameter, right? Right? This thing that I want to plot is my PDF. So this is my PDF. Okay? Yeah. I want to plot what? I want to plot x. Okay? I want to plot x over this range. 0 to 10. The PDF, this f is of the type log normal distribution. And this here is my knobs, right? This is my parameter. Yeah. That makes sense? Okay. Once again, I have to tell this is functional programming. You cannot talk to the computer without putting things into a function. Even to say, I'm thinking about log normal distribution, you have to put it into a function. So that function says, hey, wake up. I want to look at log normal distribution. Log normal distribution with parameter 0.7 and 0.1. I want to look at the PDF. That's my distribution function, right? There's PDF. PDF is cumulative. I want PDF, which is non-cumulative version. So I want the PDF of normal distribution with this parameter, PDF of this function with this parameter over the range from 0 to 1 to 10. Okay. Now, okay, I'm going to erase this. So this is what I did. Okay, so it's very peaky. It goes all the way. So this is where you have another option to say, I want range or plot range, plot range. Okay, right. Okay, so sometimes it's sort of like get smart and say, oh, maybe I just want to look at the details. So I want plot range. Now, what if I don't want the PDF? What I want is a cumulative distribution function. So I go CDF, right? That's CDF. So this is something you know already. Okay, right? Now watch this. Watch this. So this is PDF of a log normal distribution with this parameter. I'm just plotting range from 0 to 10. Okay. Now I'm going to do it again, except instead of just this guy, okay, just this guy, I'm going to plot two things. The other thing is also PDF, but I'm going to use normal distribution with parameter 4.3 and 0.4. Okay, so I'm plotting two lines, right? See that? So normally, I told you before, right? You get a histogram, you try to find the distribution that best fits the histogram. In this case, because it had two humps, I'm going to say, well, I can't get one probability distribution that will fit two humps. I'm just going to get one probability distribution to fit one hump, the other function to fit the other hump, and then put them together. Now, when I put them together, what happens? The area under this curve is 1. The area under this curve is 1. So the component has an area under the curve of 1, right? But I want the combination to have the area under the curve combined with 1. That's where this is. So what if I take 35% of this guy and 64% of this guy? Let's do that. So instead of plotting them separately, I'm just going to add them. Okay. So not separately now. I'm just going to add them. Okay. Now, obviously, if I add them, what's it going to look like? Like this, right? But now the area under this curve would be what? 2. That's too big. So let's make it, say, 0.35 and 0.65. Okay. This is the distribution. Actually, it turns out that this one is the best I can do to fit this. Okay, that doesn't look right, but basically that's it. Okay, so this is what we mean by mixture distribution. Okay, mixture distribution. So when I click to this function called mixture distribution, and let's go to F1, that's what it tells you. It allows, well, in our case, we actually have 2 distribution, right? Distribution 1 and distribution. Actually, it allows you to have as many as you want. So you can mix 10 different distribution as long as you give it the weight. Now, the weight actually doesn't have to add up to 1. It knows how to normalize that. So like this, for example, okay? So I define distribution as a normal distribution with default parameter, that's 0, 1, standard normal. This is normal distribution with mean 2, standard deviation 0.5. I take 2 part this guy and 1 part that guy, and I get this. See that? Okay. Yeah. Can't talk to the program unless you mention it in the function form. I'm thinking of normal distribution. Oh, that's function. I'm thinking of another distribution function. This is standard normal. So it's going to be centered around 0, 1. Basically, and that guy has higher mean, smaller standard deviation. And then I want to take 2 part of this, 1 part of that. Okay. I can take equal parts. The point is I can adjust the height of the hump. That's pretty cool, right? So what this means is that this is how you fit the mixture distribution. Now let me show you how this is done. So now, interestingly, okay, let's do this. Now I know that to choose wisely, I have to look at the range of possibility, right? The geyser cannot have negative duration. So I should use normal distribution. Having said that, in practice, if you know something that's not negative, you can still use normal distribution. It's just going to look like this. So even though technically you can have value less than 0, numerically it's virtually 0. Okay? And because normal distribution looks like a good fit, I'm going to use it. Okay? Now, how would I do that? Let me show you. Okay? So let's say this is I'm going to call mixture distribution. Okay. Right. Now, this thing asks for combination. So let's say I'm going to say one part of each, comma, normal distribution. Okay, normal distribution. And I'm going to say something like 1 and 0. So that's basically standard normal distribution. So I'm going to do this. So do this first. It's not very interesting. Okay. So mixture distribution expect two arguments. One is the weight. The other one is the component. So this make no sense because it's actually the same weight. So let's make this 2. Sorry, 0, 1, not 1, 0. Okay. And this is something like 0.5. This was the example before. Okay. That's a distribution. I define this. So if I define this, my distribution, okay, equal to this. And I want to plot, okay, PDF of my distribution X from, right? X from where to where? Say -3, -2 to 5, say. Okay. Plot my PDF. Okay. See that? Okay. Let me just make it big. So you know what? Instead of editing, I'm going to start a new line. That way you see how it progresses. Okay. So can we do this? Okay. Now change it. Okay. Right. Now I'm going to give it name. Okay. So let's call it W. Okay, let's call it W. Okay, let's see if I can do this. How about I manipulate this W from say 1 to 5. Okay, now notice I'm going to increase W. Right? So you can see that with this mixture distribution, I can allow the composition. Okay, so you can key in like I did. The distribution is this. Plot my distribution from there. Okay, just to save time, why don't I just give this to you guys in the line group? Okay, there. Just copy this. Okay, and enter. You should get this. Okay, that's in the line group. Okay, so you have this thing now. Okay, got this thing now. Okay, so now I'm not just going to move the W. I'm actually going to move this thing means. So I'm call this mean 1, and this is mean 2. Okay, and 1 going from say, I don't know, -0 to 5, and mean 2 from 1 to 5 or 1 to 6. Okay, how about this? Okay. See that? So I can move mean 1 from the left to the right. Okay. Okay. Right. What else can I do? Okay. So we got mixer distribution, equal part of this and that, and a plot. Now I'm gonna make part the weight difference. I'm gonna make the location difference. See, I have all the flexibility in the world. Let me put control placement. You're right. Okay. So yes. That's nice, right? Okay. Next. Okay. Next, I'm going to standard deviation and standard deviation 2. All right. So let's go mean, then standard deviation 1. Now standard deviation cannot be 0, so I'm going to start it to 1, 2, I don't know, 2. Okay. Okay. Oops. Right. Oh, too high. So let's make a range plot. Plot range. Oh. Okay. So obviously, if the standard deviation is low, it's going to be peaky. So let's get that. Not so not. Okay, something like that, right? So I have all the freedom in the world, so to speak. Okay. This is me. This is me doing it. This is me doing it. Now, what if I don't want to do it? I want this data. So this is data set, right? What if I want to find this, and this? How would I do it? Okay. It would be like this. Find distribution parameter. Okay. Find distribution parameter. Let's go to F1. How does it do it? The data and the distribution and the parameter. Okay, fine. So find distribution parameter. So let's put in the data, right? What's my data? So I just want the first dimension, right? All and number 1, right? This is my data. So this is this and comma. Now I'm gonna copy this thing and I put it over here. Okay, what's the difference? This is argument number 1. This is argument. Okay, what's the difference between here and here? Here, I specify the distribution, W part of this guy, 1 part of this guy. And then this thing, is up to my setting. I set it myself. So I can play with it, right? This is being played off. But instead of me, that's probability. Now I'm going to do statistical, right? Statistic. So what I do is exactly the same as before, except instead of specifying the value themselves, I just do this. Watch what happens. See that? This is my mixer distribution. Has 1 part this, has 1 part that, has all the freedom. 1, 2, 3, 4, 5 number. Based on this, computer went ahead and tried to find the best value that fits. It turns out the best value that fit this distribution of the duration of the Old Faithful is 1.8 part of this and 1 part of this. So that is mean of 4 minutes and standard deviation of 0.4 minutes. The other one is mean of 2 minutes. And so this corresponds to what we saw earlier, right? Think about it. What's this guy? What do you think is this is the long duration, right? Mean 4 minutes. 4 minutes. Yeah. Last 4 minutes. 4 minutes. Standard deviation of plus minus 1.45. The other one is 2 minutes. And they exist in the ratio 1.8 to 1. So that means there's a lot more long duration than short duration. Right? There's about 80% more. That's what this found out. Yeah? That's what this thing finds out. So this is probability. Okay, let's write the words plain text. This is probability construction. Okay, using mixture of two normal distribution random variable. Okay. Right? Yeah. So this is nice. Okay. I can also do this for the second aspect. What's the second aspect? It's a waiting time, right? Okay. Waiting time of 80 minutes. Waiting time of 54 minutes. And again, you have more long wait than short wait. Okay. Now let's put that together. Okay. This is only what? One aspect, right? One aspect. The other one is another aspect. Okay. So let's put them together. Again. Okay. This is probability. This is probability. This is statistics. Right? But this statistic is not that interesting yet. Why is it not interesting yet? Anybody? Anybody? Because this is univariate, right? So I can make something more interesting. So instead of having univariate on the duration of the wait and the duration of the geyser, let's say, okay. Again, this is what the data looks like. Okay. List plot. Okay. Let's say I have a bivariate normal distribution and another bivariate normal distribution. That'd be nicer, right? So I can fit both the duration of the wait and the duration of the water spout at the same time, right? So I'm going to do the same thing, except I won't do it separately anymore. Okay. So what am I going to do? Well, obviously, I'm going to have bivariate distribution. So let's go to binormal distribution. Okay. Binormal distribution. Now watch. I don't know what the syntax is, right? So let's go to binormal. Oh, okay. It's very easy. First mean, second mean, first standard deviation, second standard deviation, correlation. Okay. So let's do that. Actually, I'm just going to copy this just to make it life easier. Okay. Now, you may not like this, so let's call it M1, M1, M2, S1, S2, and correlation row. Okay. So that gets you one hump. Now I want two hump. So how do I do that? Just like before. Mixture distribution. Okay. So now I have this guy and I have another hump. Okay. Have another hump. Now, obviously, I have to change my indexing plan a little bit, right? Because this is what? Mean 1, mean 2, right? Of the first hump, right? So let's call this N. Or let's do this. Let's call it M11. Okay. 11, and then M12, M21, and M22. Okay. And this is S11, S12, S21, S22. So many parameters now. Okay. And row likewise, right? So this is row 1 and this is row 2. Okay. So that's my distribution. Yep. Oh, sorry. S11, S12, S21, S22. Okay. Right. So let's understand what we're trying to do. Binomial distribution. The first one has been standard deviation. This is mean, and this is the standard deviation. Right? When you look at the other axis, so this is one axis. Look at the other axis. This is the mean. This is standard deviation. If you look on top, that's the row. Okay? So that gives you bivariate normal. But I don't want one bivariate normal. I'm greedy. I want another set. And I want the weight in between. And then create a big solution. So this is as, yeah, we'll go to neural network and life will apparently look simple. Okay. So this is what I want to fit. Now let's see. I haven't done this, by the way, so let's hope it works. Okay, so this is the name of the distribution. I want to fit whom? I want to fit data to this mixed distribution. I want to find this. Let's see if this works. Okay, hang tight. Yeah, what am I saying? This would take, R or Python, 20 lines at least. Find the distribution parameter using this data based on mixture of two non-bivariate normal distribution with this parameter. So what it's going to do is this number is going to try to find the best. I don't know. Let's hope it works. Relink. Why am I? Something is not right. So let's do this. Let's it's not a recognized distribution. Hold on. Okay, let me try something. Okay, I'm gonna put some number and see if it works. Just a second, okay? I don't know why it doesn't work. Okay, and let's say I'm gonna do this and plot 3D this thing of x I don't know why it doesn't work, by the way, guys. It should work. Let me just try without the mixture distribution, see what happens. See if it works. Okay. And this should work. It's not a recognize. Something about the way I put here. Binomial distribution, bracket, bracket, bracket. Oh. Oh, what I did. I think I defined something before again. I keep doing that. Okay, let's try again. Let's try again. Let's try again. Never give up. Okay, hold on. This is terrible. Okay. Okay. Now this is one dimension. So let's say I want this to be 2-dimension, right? 2-dimension mean binomial. Why is life not difficult? Variance, covariance, matrix, mean 1, mean 2, mean 3, mean 4. Okay, I'll do this. Okay, let's go find distribution parameters of data and this. Why is this not a recognized distribution? Oh, wait a second. Have no idea, guys. It's in the bracket because it knows what this is, right? It knows what it is, but it's telling me it doesn't know what it is. It's not a recognized distribution. So there's something about my bracketing that throws this thing off. It's in the bracket. It's always bracketing. It's always bracketing. Now let's say that's kind of weird, really. Okay. Tell you what, I know what we can do. We can generate it and then we can test it. Okay. So just like here, I know now. D, okay, is equal to distribution, mixer distribution of this, and I'm gonna get mean 1 and okay. Okay, I start over. Okay, watch me. What I'm going to do now is I did 2 things at once. I should have done that. I'm going to make this bivariate distribution first. Okay, and once I get this working, then I can fit the data. Okay, so it has to be a bivariate distribution. So we got this. This is univariate distribution. Okay, so now I'm going to repeat the same thing. I'm going to repeat the same thing, except it's going to be binomial distribution. Okay. And then mean 1 and mean 2. Then standard deviation 1, standard deviation 2, and I'm going to forget about this mixture thing. I'm going to make there. Okay. So standard deviation 2, and correlation, let's make it 2.5. Okay. My distribution, that's my distribution. And I'm going to plot 3D X and Y. And my X and my Y. Okay. Good thing I don't need. Okay. Okay. Now I got my bivariate distribution. Okay, I got my bivariate distribution. Now let's see if I can make this mixture of bivariate. So I'm gonna make this one, and I'm gonna make this another one. Oops. I give this to you at the end, guys. Don't worry, because if I struggle, then you must. Mixture, distribution, right? One part, comma. Okay. Now, so now I got mixture distribution. I'm gonna make it 1, 1, 1, 2, 2, 1, 2, 2, 1, 1, 1, 2, 2, 1, 2, 2. Okay. 1, 1, 1, 2, 1, 1, 2, and 2, 1, 2, 2, 2, 1, 2, 2. Okay. Right. Okay. So now I got bivariate. I can create bimodal. Okay. So now I can do this, right? Now I can do this. So now I can get something that looks like I've got 2 nodes. Okay. Yeah, fine. And okay. And I can say R generate data equal to random variate D, random variate my distribution 1,000. Okay. Okay. So in other words, I'm not just gonna plot this. So I'm just gonna say so let's give it something more interesting, like mean is 2, 4. Okay, is that interesting enough? Okay, so I got this data set. Let's see if my gen data is correct. I got my gen data. Okay, so I generated this. Doesn't look that interesting, but anyway, it's got 2 nodes now. Okay, it's got 2 nodes. And now I'm gonna say this is my distribution. Okay, find distribution parameters of this guy, comma, this guy. Yes. Okay. Yeah, apparently I did something wrong with the bracket. Okay. So I generated this myself. Okay. So I was trying to, and it's a found out that the first one is 0.38. Okay, so these are all the estimates. These are the data with a hat. Okay. Yeah, I think I know what happened. Every time I copy from a page and the bracket comes with it, apparently it's a bit funny. So I have to type it myself. I don't know. Anyway, so this is the value that it estimates. Okay. This is the value that it got. Mean the first mean 1 is 0, mean 2 is 2. It estimates as 0.038 and 0.199. So it didn't get exactly right. It didn't get exactly right. If I did this for 1,000 times, maybe, a lot more data point, I would get this. The point is now, okay, I'm just going to forget about the old guys now, but let's see. Let me try one more time. Okay. Oh, row 1. Okay, just now I did allow the row 1 to go. Okay. So I can set. So it didn't have a good accuracy at the moment, but that's what it means. Okay, so it gets some kind of number. It doesn't converge within 100 iteration. So what I have to do is to actually allow for set a different default. Okay, but it's something like that. So if I did this, and my gen data, I list plot my gen data. Okay. Okay. This is what I generated. Okay. Now what I want to do, and because I kind of messed this up, I'm not going to, waste class time doing it. But let's say what I want to do is, I know that I generate this from 2 lumps. But the 2 lumps are so close together, I know that the neural network or the cluster analysis is going to fail. So something like this, I would expect it to fail. But what I'm going to do is, what if I make it a little bit further apart? Let's say something like start from 4. Okay. And something like that. Okay. Let's say I do this. Okay. If I did this, and I generate list plot, it should have a good separation. Okay. So again, this node I make up from scratch. This I make from scratch, right? And I make 2. What I expect is that when I go to the clustering analysis next class, the computer is going to put this guy together. No problem. Okay, no problem. And you will see that by doing this, by controlling my generation, if I make it really far apart, okay, if I make it really far apart, or I make the standard deviation really small, okay, now, this is another way I can do this. Okay. So this thing, I do list plot again. Yep, it's even better separate. So there's gonna be like a whole empty space here where nothing happens, and I'm gonna get now. What I'm going to do, this is my plan. And, sorry, it didn't go smoothly, so I'm going to carry this exercise I think later at some point. What I'm going to do is my plan is, okay, my plan is to have a generating function that would create, say, 5 clusters. So I can have something like, let's say, 2 dimension. I can do this. I can say, it's 1 cluster, another cluster, this is another cluster, this is another cluster, this is another cluster. Okay. The reason we would do this is because as I increase the distance between these 2 clusters, shown before, the model should pick up that there are 5 clusters. As I use them, for example, I make the cluster, the variance higher. Now it's going to have a harder time. What's going to happen is, and this will depend on algorithm. Some algorithm will measure distance as cluster. So what it would tend to do, and we'll see how this happens. It will probably do something like this. 1 cluster, 2 cluster, 3. Okay? This is called a metric distance space. So this is close to the spot. On the other hand, there's actually what's called density phase, where instead of measuring the distance, if this guy is far from that guy and this one is close to here, it's able to pick up the fact that this is contiguous. So what I want to do basically is, and I was actually hoping to get it done, within class today. It's something like this. Okay, little pockets of bump in probability. Okay, and try to be able to arrange it, moving it around and orient it and so forth. And once I press the button to generate it, okay, this data set here will be something we know because we already know what the mean is. Okay, so forth, right? So we know that if it's close together, something like this, how would it fail or succeed? Okay, and it will have to fail. We saw earlier that here, it doesn't know. That's the difference between the neural network and probability distribution function. Probability distribution function knows that it has to be a mixture of these two things. Yeah. So if it's close together, it gets something like this. Okay? And you ask Mathematica to find parameter for a mixture of 2 distributions. It's going to be able to find one here, one there. But when we go to unsupervised machine learning, it doesn't assume any form. It's just going to say, hey, wait a minute, it looks like to be the same lump. You know what I mean? So even though I can generate, say, 1 lump, 2 lump, and 3 lump, if I put these 2 lumps close together, and this lump far apart, the clustering algorithm is going to think that there's 2. Because it doesn't assume the function. That's what I'm trying to get at. Okay. So that would be the difference, the key difference between statistical or probabilistic modeling and non-probabilistic modeling or using machine learning. Machine learning does not know because you haven't chosen the function. Okay. So it would say something like lock things together. Okay. Whereas with probabilistic modeling, I'm saying that in that thickness, there are actually 2 lumps. Okay? They mix together. We'll find it. And it's going to find the best mix. So it would try to find it because this shape is definitely not normal distribution. And you tell it that there are 2 of them, this picture of 2, it's going to, oh, you know what, this is one. Okay? So there is the difference between probabilistic modeling and general non-probabilistic. The question is, can you say one is greater than the other? I would say that now, even though it would be very nice for us to say, this big map, I can decompose it. I'm very clever. I can decompose it into a mixture of 2 normal bivariates. that additional value usually doesn't help much in analysis. Because at the end of the day, does it matter that let's say this is a client group, this is another client group? You can still treat them as two, right? Even though parametrically it's so elegant to say, oh, this is actually two populations fused together. But precisely because they fuse together so well, you can't tell them apart. There's no need to tell them apart. Okay? So nowadays, the benefit of doing this kind of analysis would outweigh the fact that you can't make this clear statement. Oh, there's a normal distribution, there's a Gaussian, there's a gamma, you know. And that's why non-probabilistic modeling has taken over. Okay? So it goes to the application. So even though, you know, by the nature of the course, I can base the entire course on statistical modeling, and that would be a legal way of teaching this class, right? It's not the modern way. It's not the, yeah. It would have been the standard way 20, 30 years ago for two reasons. Number one, the algorithm, that minimization of the error, it didn't work so well. Again, we didn't have this GPU and all that. So the neural network or machine learning or deep learning, all kind of stuff is not available. Number two, even the simple one that was available at my time, when I was your age, it was very hard to gain acceptance. Okay, people, business people, you know, clients for your consultancy project, whatever, they grew up learning statistics. So if I'm going to tell them that based on analysis, your client is in a two blocks. 20 years ago, that was very difficult to tell. That people who want they can't understand. But if I say it's a mixture of two binary normal, yeah, but nowadays the atmosphere, I guess the environment, acceptance for non-parametric statistics is not real. Okay. So with that, I haven't got a homework. I think you can play more with it with the previous homework. I certainly will play more with mine. Again, I'm gonna create this from 2 lumps into 5 lumps. I'm gonna control how they get together and so forth, right? My apology that it didn't go smoothly. I was gonna try to do it from scratch just to convince you how easy it is. It is easy. I just screwed up somewhere. Okay. So this one I'm just gonna save as is and give it to you guys, and you can play with it however you like. I'm not even gonna name it. Okay. Why can't I save it? Okay, so yeah, you can play with this however you like. And if I were mean, well, I really wanted to have you guys go through this with me and maybe turn in your version of this data generator, but seeing that I myself couldn't get it to work, so I can't really in a good conscience make it your homework if I can't really do it myself. Okay, so go play with it. Go play with it. I'll see you guys next. Yeah, no homework for now. And okay,ครับ. Yeah, come in.